Imagine, just for a moment, that you are resting completely flat against the warm, soft sand of the ocean floor.
Okay, so totally still.
Right, perfectly
Yeah.
still. And the sun is just beginning to set over this really vibrant Indo-Pacific coral reef.
Ah, that sounds beautiful.
It is. It really is. And, from your vantage point, looking up through the water, you can see these long kind of dancing shadows of gold and turquoise filtering down.
Like that perfect late afternoon light.
Exactly.
Yeah.
But you're not just a passive observer here watching the sunset. You are perfectly seamlessly hidden in this environment.
Blending right in.
Yeah. Your skin is incredibly thick, heavily armored, actually. And if something were to brush against it, it would feel exactly like coarse, heavy grit sandpaper.
Ouch. Like really rough.
Oh, incredibly rough. And running right above your eyes, forming would look like these permanent angry eyebrows or these heavy ridges of hardened, bony spikes.
Angry eyebrows. I love that image.
You're quite a look.
Okay.
So you are this massive, heavy creature, yet you are completely invisible to everything swimming above you.
Because you're blending flawlessly into that dappled light and the gray-brown mud of the seafloor, right?
You got it. And perhaps most importantly, you are being incredibly patient.
Which is hard, you know? The discipline required to remain that motionless in such a highly active ecosystem is staggering.
It really is. I mean, you are lying perfectly still. Your mouth is pressed firmly against the fine silt, but you aren't choking on the sand.
That's a neat trick.
Yeah, instead, you are actively drawing in this crystal clear water from a built-in biological snorkel.
Wait, a built-in snorkel?
Yeah, located right behind your eyes. So you are gently, rhythmically pumping that clean water over your gills.
Allowing you to breathe continuously without moving a single major muscle.
Exactly. You are just waiting. And then suddenly, you feel it.
Feel what?
A microscopic, almost imperceptible tingling sensation ripples across your wide, rounded snout.
Oh, wow.
And it isn't a sound wave echoing through the water. It isn't a chemical scent drifting on the current. It's a faint, invisible electrical pulse.
An electrical pulse.
Yeah, it's the signature coming from the beating heart of a crab that is buried deep in the sand, completely out of your visual sight.
Wow, so that singular spark is the catalyst. The waiting is over.
The waiting is absolutely over. In a fraction of a second, the absolute stillness of the ocean floor just shatters.
The hunt is on.
Oh, yeah. With this sudden explosive burst of kinetic energy from a powerful, heavily muscled tail, a tail that looks exactly like it belongs to a great white shark, you launch forward.
A shark tail.
Yeah, and you violently pin the shifting sand down with your wide, heavy head, trapping that hidden target.
Oh, I can almost hear it.
Well, there's a loud, echoing crunch that reverberates through the water as you easily flatten the crab's thick, armored shell.
Incredible.
You, my friend, are one of the most magnificent, mysterious, and structurally bizarre creatures hiding in the global ocean. You are the bow guitarfish.
Welcome back to Saltwater Stories. We're so glad you're here with us.
We really are. And today's entire journey is all about unraveling the puzzle of this incredible animal, the bowmouth guitarfish.
Because honestly, this creature looks and operates like a prehistoric sea dragon.
It totally does. And it holds some of the most fascinating biological engineering secrets on the planet.
It really does. And to set the baseline for just how sophisticated this animal's biology is, I have another little story.
Oh, I love these. Lay it on me.
So picture another scene on that exact same reef. Imagine a tiny flatfish.
Okay, a little flatfish.
Yeah, and it is perfectly camouflaged against the dark, complex background of the ocean bottom. It is holding perfectly still, meaning it's making absolutely no acoustic noise.
Like totally silent.
Totally silent. And it's tightly regulating its bodily functions, so it's giving off essentially no chemical scent in the water either.
So it's basically invisible, silent, and odorless.
Exactly. For all intents and purposes, it is the ultimate hide-and-seek champion of the reef.
Okay, I'm with you.
Yet a massive shadow glides slowly over the coral, and it stops exactly, and I mean with millimeter precision, above the hiding spot of that tiny, silent fish.
Because, as we kind of touched on in the opening, the bowmouth guitarfish possesses a literal, real-life superpower.
A biological superpower.
Yeah. Scattered all across its incredibly wide face and snout are hundreds of tiny jelly-filled pores.
They're called the ampullae of Lorenzini.
Right, the ampullae of Lorenzini. And they act exactly like a high-tech biological metal detector.
Which is just wild to think about.
It is. But instead of finding, a lost wedding ring on a beach, This creature is actively sensing the tiny spark of electricity generated by the hiding fish's beating heart.
Just its heartbeat.
Its heartbeat and its firing muscles. It's sensing the actual electricity of life.
That level of sensory perception is fundamentally alien to human experience. We just don't have the biological hardware to process the world through an electromagnetic field.
We really don't. We rely so much on what we see and hear.
Exactly. And, to understand how an animal develops a sense like that, you have to look closely at its physical shape. How does a creature end up looking like this, and what exactly is it?
That was the very first question I had when we started exploring this animal's story.
Because it is a confusing-looking fish.
Oh, incredibly. When you look at a photograph of the bowmouth guitarfish, it legitimately seems like a creature built out of spare parts from an evolutionary chop shop.
That is the perfect way to describe it.
Right.
Yeah.
Because you have the incredibly wide, flattened, disc-like front half of a stingray.
Like a classic ray shape.
Yeah. But then that anatomy transitions seamlessly into this sleek, heavily muscled body with towering dorsal fins and the sweeping asymmetrical tail of a shark.
It's literally half ray, half shark.
It is. And because of that confusing appearance, it has a bunch of nicknames, like the mudskate, the bow-mouthed angelfish, and very commonly the shark ray.
The shark ray, which makes sense.
It does, but it also brings up a massive point of confusion.
Yeah.
Because biologically speaking, this animal is classified rigidly as a ray.
It is a true ray.
But if it swims exactly like a shark, with that powerful side-to-side tail sweep, rather than flapping its pectoral fins like a manta ray, why do we insist it's a ray?
It's a great question. And it comes down to a very strict biological rule. It's all about the specific placement of the gills.
The gills.
Yeah. If you look at any true shark, whether it's a massive great white shark or a tiny leopard shark, their gills are always on the sides of their head.
Oh, right, like those classic slits you see on the side.
Exactly. But in rays and skates, evolution has shifted those gill slits entirely underneath the body, on the belly.
Ah, so it's all about the location of the breathing holes.
Precisely. So it doesn't matter how the animal propels itself through the water. If you look underneath the flattened head of a bowmouth guitarfish, that is exactly where you will find the gills, sitting flush against the sand.
So that one feature makes it a ray, no matter what its tail is doing.
You got it. It belongs to a group that includes other guitarfishes and sawfishes, all sharing that bottom-dwelling belly gill design.
Okay, that makes sense. But what really blows my mind is what is holding all of that specialized tissue together?
The skeleton.
Yes, because we need to establish the scale here for you guys listening. The bowmouth guitarfish is massive. Mature adults can grow up to nearly 9 feet long and weigh over 300 pounds.
That is a very large, dense predator.
It is. But it does not have a single bone in its entire body.
Not one.
How does that even work?
Well, like all sharks and rays, its entire skeleton is made of cartilage.
Right, which is the exact same flexible, rubbery stuff that gives our noses and ears their shape.
Exactly. Just wiggle the tip of your nose, and that's what a 300-pound shark ray's skeleton is made of.
Which is hard to wrap your head around. How does an animal that heavy support itself without hard bones?
It comes down to staying afloat.
Yeah, I was trying to come up with a good way to visualize this, and I think building a kite is a perfect analogy.
Oh, I like where this is going.
Right, so if you tried to build a giant sweeping kite using heavy, solid oak sticks, the kite would be way too heavy.
It would never catch the wind.
Exactly, it would just crash straight to the ground. But if you build that exact same kite using lightweight, highly flexible rods, it drastically reduces the weight.
Allowing it to glide effortlessly.
Right. And cartilage acts exactly like those lightweight rods for these marine animals.
That's a brilliant way to frame it. Because buoyancy, or floating, is a huge issue in the ocean. Most regular fish have something called a swim bladder.
An internal balloon, basically.
All right, a gas-filled sac that lets them hover in the water without using energy. But sharks and rays don't have swim bladders.
Oh, so if they had heavy bone skeleton.
They would sink like stones the moment they stop swimming.
Wow. So the cartilage skeleton is this massive evolutionary workaround to keep them from being too heavy.
Exactly. It saves them a ton of metabolic energy.
But, and here's where I kind of push back on that. Having a soft, flexible skeleton creates a massive physical vulnerability, doesn't it?
It certainly does.
Because cartilage doesn't offer the same rigid protection for your internal organs that a thick rib cage of bone does.
You are absolutely right. But nature rarely leaves a vulnerability unaddressed. Because the inside is soft, the outside of the bowmouth guitarfish is reinforced to an astonishing degree.
It's basically an armored tank.
It really is. If you were to run your hand along its back, you wouldn't feel smooth fish scales. The skin is covered in structures called dermal denticles.
which translates to skin teeth.
Skin teeth, exactly. Though teeth is almost an understatement. They're literally made of the same stuff as human teeth, complete with pulp, dentine, and a hard enamel cap.
That is so weird to think about, being covered in thousands of tiny teeth.
It creates an incredibly tough, abrasive barrier.
And what's wild is that the bowmouth guitarfish takes these denticles to an extreme. We mentioned those angry-looking eyebrows earlier.
The heavy ridges over the eyes.
Right, and running down its back. Those aren't just bumps. Those are actually giant modified skin teeth that have grown into actual hardened armor spikes.
And those spikes serve a very serious purpose. You have to remember, these animals live in habitats patrolled by massive, highly aggressive predators like tiger sharks.
Which are terrifying.
Yes. And if a large tiger shark decides to investigate arresting guitarfish as a potential snack, the guitarfish doesn't just try to swim away.
No, it stands its ground. I was reading about this, and it's wild. It will actively arch its back, exposing those heavily armored spiked ridges.
And if the predator gets too close?
It aggressively headbutts the attacker.
Think about the physics of that. A tiger shark relies on its highly sensitive snout to hunt.
Right, and the guitarfish just violently rams a crown of hardened spikes directly into the shark's most sensitive area.
It's a phenomenal deterrent. The tiger shark quickly realizes the meal isn't worth the risk of being blinded or injured, and it swims away.
The defensive engineering is just a masterpiece.
It really is.
But, surviving predators is only half the battle. The engineering marvels of the bowmouth guitarfish go way beyond just its external armor.
Oh, absolutely. Surviving day-to-day on the ocean floor is a huge challenge.
Right, because there is a fundamental, almost comical problem with its body plan.
The breathing problem.
Yes. If your mouth and your delicate gills are located strictly on the underside of your body, and you spend your entire day resting flat against the muddy sand.
How do you actually breathe without suffocating yourself?
Exactly. If I laid completely face down on a beach and tried to take a deep breath through my mouth, I would instantly choke on a lungful of sand.
You'd be coughing for hours.
Right. And if a bottom-dwelling ray breathed by opening its mouth, it would pull all that silt and dirt directly into its delicate pink gills.
They would clog instantly.
So how do they bypass the mouth entirely?
It's all thanks to a specialized structure called a spiracle.
A spiracle.
Yeah. If you look at the top of the guitarfish's head, right behind those angry, spiky eyes, you will see two prominent holes.
Like blowholes on a whale.
Kind of, but these are actually an evolutionary remnant. Millions of years ago, in ancient jawless fish, they were just regular gill slits.
Oh, really?
Yeah, but as animals flatten out to live on the bottom, those front gill slits migrated to the top of the head and changed their job completely.
They became those built-in snorkels we talked about earlier.
That is the perfect mechanical analogy. While the mouth is pressed safely into the sand, these spiracles on top of the head are actively working.
Pumping the water. Right. They have strong internal muscles that actively draw in clean, clear water from above.
And then that fresh water is routed down internally over the hidden gills on the belly and pushed out.
So it's basically a highly efficient internal plumbing system.
Exactly, allowing it to breathe perfectly while completely motionless in the mud.
Which is critical because staying motionless is their whole hunting strategy.
Yeah.
And they need a lot of energy because of what they eat.
Their diet is intense. They are categorized as durophages.
Which means hard eaters. I love that term.
It's very accurate. They specialize in hunting prey with incredibly tough armor. Crabs, spiny lobsters, thick clams.
Which immediately presents another massive challenge. We just said their skeleton is made of soft cartilage.
Right.
So how does an animal with a rubbery jaw generate the immense crushing force needed to shatter a thick clamshell without breaking its own face?
It's an engineering paradox.
It really is, because if you look inside the mouth of a great white shark, you see sharp, triangular teeth designed for slicing soft tissue.
Like surgical scissors.
Right. But the teeth of the bowmouth guitarfish look completely different. They are large, rounded, and arranged in these thick bands that look like rolling cobblestones.
They don't function as blades at all.
No, they function exactly like heavy, rolling nutcrackers. The jaw is designed to shatter and grind.
But to operate those crushing plates, the jaw muscles have to exert an astronomical amount of pressure. A normal cartilage jaw would just buckle under that stress.
So how does it survive the bite?
The jaw undergoes a process called localized calcification. The outer layer of the cartilage is wrapped in thousands of tiny, hardened blocks called tesserae.
Like thick ceramic tiles paving a floor.
Exactly. They provide a rigid outer shell that distributes the initial impact of the bite.
But even that isn't enough to handle the force of cracking a thick lobster shell, right?
No, the true genius is what happens deep inside the jaw cartilage itself. There are tiny internal struts known as trabeculae.
Trabeculae.
Yes. It's a network of hardened bands running right through the soft cartilage core.
And the reason I love this detail so much is that it is identical to modern human architecture.
Oh, the skyscraper analogy.
Yes, when engineers design a giant skyscraper, they don't just pour solid blocks of concrete. Solid concrete is brittle. Under huge stress, it would snap.
Right, it can't bend.
Exactly. So instead, they embed highly flexible steel rebar inside the concrete. The steel flexes and absorbs the tension, while the concrete handles the compression.
And the trabeculae in the jaw act exactly like that steel rebar.
It's just wild. They absorb and distribute that massive kinetic shock, ensuring the jaw never splinters when it crunches down.
It is a stunning example of nature inventing complex engineering long before humans did.
Totally. But the engineering doesn't stop at the mouth. Once that hard-shelled meal is pulverized and swallowed, it has to be digested.
And this might be my favorite part of their biology.
The Tesla intestine.
Yes, it is brilliant fluid dynamics. If you look at the intestine of a human, or most animals, it's a long, looping tube.
Right, because you need length to give the body time to absorb all the nutrients from the food.
Exactly. But the guitarfish has a distinctly short, compact, almost stubby intestine.
Which seems like a problem.
It would be, except inside that short tube is a complex structure called a spiral valve.
And the diagrams of this look unreal. It looks exactly like a tightly twisted water slide, or like a spiral staircase made of tissue.
So when that crushed slurry of crab shell and meat enters, it doesn't just shoot straight through.
Right, it's forced to navigate this incredibly tightly winding path, swirling around and around each layer.
Which dramatically increases the surface area for nutrient absorption while keeping the overall size of the organ very small.
It saves precious space inside the animal's heavy body.
And you called it the Tesla intestine for a very specific reason.
Yeah, the historical parallel here is mind-blowing. In 1920, the famous inventor, Nikola Tesla, actually patented a mechanical device called a valvular conduit.
A very specific type of pipe.
Right. It was designed to significantly slow down and control the flow of fluid using precisely angled winding internal loops without using any moving parts.
And evolution had already perfected that exact hydrodynamic design millions of years earlier inside the gut of a ray.
It's amazing. Modern engineers actually study the shape of this intestine today to build better, clog-free pipes for city infrastructure.
Nature is the ultimate testing ground.
It really is. So now that we understand how it breathes, how it crunches shells, and how it digests, we need to look at where this is all happening.
The ecological stage, so to speak.
Right. Where and when is this predator utilizing these tools?
Well, let's set the geographical scene. They live primarily in the warm, shallow, tropical coastal waters of the Indo-West Pacific.
So places like the Red Sea, the coast of East Africa, over to the lagoons of Southeast Asia and Australia.
Exactly. And when we think of a coral reef in those areas, we usually picture a visual wonderland. Bright coral, darting fish, gentle anemones.
Very peaceful and serene.
Right, but that completely misses the acoustic reality of these environments. A thriving Indo-Pacific reef is incredibly loud.
Oh, it's deafening. If you drop an underwater microphone into a healthy reef, you don't hear peaceful silence. You hear a continuous, overwhelming crackling sound.
Like thousands of dry twigs snapping at once.
Or like thick-cut bacon aggressively sizzling in a frying pan. It's so loud.
And that noise is entirely biological. It's made by massive colonies of tiny invertebrates called snapping shrimp.
And I want to pause on this because the physics of snapping shrimp are insane.
They really are. They have one highly specialized, oversized claw.
And when they snap that claw shut, the water moves so fast that the pressure drops, and it instantly boils a tiny bubble of water.
A cavitation bubble.
Yes. And when that bubble collapses a microsecond later, it produces a shock wave, a loud crack, and even a microscopic flash of light that reaches the temperature of the sun's surface.
Wait, really? The surface of the sun?
Yes, just for a tiny fraction of a second.
Yeah.
But millions of these shrimp are doing this constantly, creating that wall of sound.
It's how they communicate and stun small prey. And scientists actually use that volume to measure how healthy a reef is. A loud reef is a healthy reef.
So the bowmouth guitarfish lives its entire life fully immersed in that bustling, deafening noise.
But if you swam over that reef during the day amidst all that chaos, you probably wouldn't see a guitarfish moving at all.
Because they are strictly nocturnal hunters.
Exactly. While the sun is shining brightly, they power down, they settle into the sand and rely entirely on their camouflage and armor to stay hidden.
Which makes perfect biological sense when you think about their eyes. Because their eyes are right on the top of their head.
And the tropical sun reflecting off shallow water creates an intensely harsh glare.
Right, so if they can't close their eyelids like mammals do, how do they deal with that blinding light all day?
They have a highly specialized built-in sun visor.
I love this feature.
It's an intricate structure in the eye called a pupillary operculum. It's a dynamic flap of tissue that comes down over the pupil.
Acting exactly like a pair of high-end polarized sunglasses.
Exactly. It blocks out the harsh glare, so they can still monitor the water above them without burning their retinas.
Brilliant. And their eye defenses go even further than just light protection.
Yeah.
Because the eyes are a major weak point during a fight.
Oh, definitely. If a tiger shark attacks, or if they are wrestling with a huge crab that has sharp, pinching claws,
They deploy a drastic mechanical defense. They literally retract their eyes.
they pull them right into their skull.
Yeah. They have these incredibly strong muscles attached to the eyeball, and they sink their eyes deep beneath those heavy armored ridges.
It keeps them from getting punctured or permanently blinded during close quarters combat.
They prioritize the safety of their senses above all else. But once the sun goes down and those long shadows stretch across the reef.
The whole behavioral profile changes. The resting phase ends, and the guitarfish wakes up.
It lifts that heavy body off the sand and uses that massive shark-like tail to glide effortlessly.
And this is where we see the culmination of all its sensory hardware. It uses a beautifully complex, 3-tier hunting sequence in the dark.
Right, it doesn't just swim around hoping to bump into a crab.
No, the first layer is chemical. It uses its highly developed sense of smell.
As they grow into adults, their olfactory bulbs expand massively. They become super sniffers.
They can detect the faintest chemical trails of drifting amino acids released by prey, even from great distances.
So the smell is the long-range targeting system. It gets them to the right general neighborhood.
Exactly. And as it follows that scent and gets closer, it engages the second layer, the lateral line system.
And the lateral line sounds like science fiction. It's a network of tiny, fluid-filled canals running just underneath the skin, all along the sides of its body.
Inside those canals are microscopic hair cells.
And it functions remarkably like a spider sitting in the center of its web, right?
That's a great comparison. The spider can't see the fly, but it feels the vibrations on the silk.
Right, the lateral line feels the microscopic pressure waves displacing the water. So whether it's a fish swimming nearby or a crab scurrying, the ray can feel it.
So smell gets it to the neighborhood, the lateral line gets it to the right house.
And then comes the final pinpoint precision strike.
When it's hovering right over the target area, it switches entirely to those jelly-filled pores, the ampullae of Lorenzini.
The biological metal detector. It sweeps its broad head back and forth over the sand, feeling for the microvolt electrical field of the prey's muscles.
Even if the water is completely pitch black or clouded with mud, rendering vision totally useless.
The guitarfish knows the precise mathematical coordinates of where to drop its heavy head and pin its meal.
It is a flawless execution of sensory input.
It really paints a picture of an animal perfectly adapted to its world, which naturally brings up a profound question.
How do they reproduce?
Yes, because if this creature requires such heavy armor and specialized tools just to survive, how does a baby guitarfish make it in an ocean full of predators?
It's a huge challenge, because you might think they just lay thousands of tiny eggs in the sand, hoping a few survive.
But laying defenseless eggs on a loud, busy reef filled with hungry crabs and fish is incredibly risky.
The mortality rate would be staggering. So they evolved a completely different strategy. It's called oviviparity.
Oviparity.
Yes. The mother does produce eggs, complete with protective casings, but instead of laying them externally on the seafloor,
She keeps them safely inside her own body.
exactly, the embryos develop entirely inside the mother, insulated from the chaos and predators of the reef.
Now, unlike mammals, there's no umbilical cord providing nutrients from the mom, right?
Right. Instead, each tiny pup is attached to its own massive, incredibly rich yolk sac inside the egg casing.
So the mother provides a safe room, basically, and they consume the yolk over many months.
And once they're fully formed, the eggs actually hatch internally.
And she gives birth to live pups.
Yes, a litter of live, fully independent miniature predators. usually between 2 and 11 at a time.
But the most crucial detail here is the timeline and the size of these babies. The gestation period is nearly a full year.
12 months of carrying them.
When they are born, they are exceptionally large. They can be up to 20 inches long the moment they enter the water.
Nearly 2 feet of heavily armored shark ray.
That massive size gives them an immediate survival advantage, because most reef fish simply have mouths too small to even try to eat a 20-inch spike-covered fish.
Size is a great deterrent, but it isn't absolute immunity. They are still vulnerable to larger sharks.
Right, they still need to hide. Which brings us to their coloring, which I found fascinating.
Their juvenile camouflage.
Because adult guitarfish are a muted grayish-brown color to blend into the muddy sand, but the newborn pups look radically different.
They are born very dark, with bright, stark white spots and bold black bands.
And I was debating the logic of this. Wouldn't having bright white spots on a dark body make a baby fish stand out way more?
It seems counterintuitive, like wearing a neon sign.
Exactly. If the goal is camouflage, why be so high contrast?
You have to look at where the pups live. They don't stay on the open sand flats. They immediately seek out visually chaotic habitats.
Like the dense, tangled root systems of coastal mangrove forests?
Exactly. And that changes the lighting entirely.
Because when the bright tropical sun filters down through the dense leaves and the interlocking wooden roots, it creates a chaotic pattern of bright, dappled light piercing through deep shadows.
Precisely. It requires a strategy called disruptive coloration.
So the bright white spots perfectly mimic the isolated flecks of intense sunlight hitting the dark bottom.
And the dark background of their skin mimics the deep shadows cast by the roots.
So when a predator like a barracuda swims by, its brain can't process the outline of a fish.
It just sees a confusing jumble of light and shadow and completely fails to recognize where the guitarfish begins and ends.
It's a biological optical illusion. That is so cool.
And as the pups grow up and put on mass, they eventually outgrow the safety of the mangroves and move to the open sand.
And as they do, their genetics dictate that those bright spots gradually fade away, transitioning into that adult grayish-brown counter shading.
Evolution has accounted for every single stage of this animal's life.
It really has.
Yeah.
And, examining how these pups begin their lives brings us to a very specific, deeply touching real-world story.
Yes, a sequence of events that connected marine biologists across the globe.
It really highlights the modern reality of this species, because this incident begins across the Pacific Ocean off the eastern coast of Taiwan.
The reports detail how a large, pregnant mother bowmouth guitarfish was accidentally caught in a commercial fishing set net.
And just to clarify, these commercial nets are absolutely not trying to catch guitarfish. They are targeting smaller schooling fish.
But because guitarfish live their entire lives in these shallow coastal waters, their habitat overlaps heavily with human fishing activity.
Right. It's a phenomenon known as bycatch.
Yeah.
And it's devastating.
It is one of the biggest threats to marine life globally.
So this massive mother is entangled and brought to a local holding facility in Taiwan. And one of the local conservation partners, a man named Fred Fan, was monitoring the situation.
And one morning, the team walked in to check on the holding pool.
And they received the shock of a lifetime. Swimming around the perimeter of the pool were 9 miraculous, live, fully formed pups.
The stress of capture, or maybe just the natural timing, caused the mother to give birth right there in the concrete pool.
Finding 9 live pups in one place is a staggering event for conservationists.
Right.
It's incredibly exciting, but also entirely daunting.
Because it presents an immediate logistical and ethical challenge.
Right. And I initially had the same thought many people might have. Why couldn't they just carefully scoop the pups up, drive to the beach, and gently release them back into the ocean?
The teams on the ground had to do a rigorous risk assessment, and the local waters in that region lacked established marine protected areas.
The density of commercial fishing nets was just too high.
If they released 9 naive juvenile pups back into that exact area, the statistical probability was that they would swim straight back into another net within days.
The mortality risk was simply too high for a species that is teetering on the edge of localized extinction.
So Fred Fan and the Taiwanese teams made a massive, generous decision. They officially donated the entire litter for a global conservation and breeding program.
They knew that accredited large-scale aquariums possessed the specialized veterinary expertise needed to raise these complex animals safely.
Which triggered a massive international logistical effort. Transporting delicate marine life across the globe requires precise control of temperature, oxygen, and filtration.
And late one night, after meticulous planning, the pups arrived safely from Taiwan to the Seattle Aquarium's off-site animal care center.
And because 9 rapidly growing pups need a tremendous amount of space, a coalition of aquariums across the U.S. stepped in to help.
Facilities like the Georgia Aquarium, the Shed Aquarium, and Disney's animal care teams all collaborated to provide permanent homes for these pups.
And the updates from the Seattle Aquarium, which kept a young female pup, are just wonderful.
They really are. She is thriving and growing incredibly fast. And she apparently loves to eat, displaying huge energy at feeding time.
And here is where the biology we discussed earlier comes full circle, because she needs to constantly crunch hard things to maintain those rolling, reinforced teeth.
She can't just be fed soft fish fillets. The care team feeds her a highly specific diet of restaurant-quality, sustainably sourced whole seafood.
Whole Dungeness crab, intact spiny lobster, and Pacific white shrimp, shells and all.
The dedication is amazing. If the seafood isn't high enough quality for a human to confidently eat at a restaurant, they absolutely will not feed it to the animals.
It's inspiring, but we do need to zoom out from this one successful rescue and explain the broader context.
Why does this massive international rescue matter so much? Why save every single individual pup?
Because the sobering reality is that the bowmouth guitarfish is in serious trouble in the wild.
The Global Authority on the Natural World, the IUCN, currently lists the species as critically endangered.
That is the highest risk category an animal can be in before it is declared extinct in the wild.
Global populations have plummeted by more than 80% in just the last few decades.
And the threats driving this are severe. As we discussed, bycatch in unselective fishing gear is a massive factor.
Because they are large, heavy, and covered in those rough dermal denticles and giant thorny spikes, they get hopelessly tangled in nets almost instantly.
They can't slip through the mesh.
But accidental bycatch is only part of it. They're also intentionally targeted by commercial fisheries.
The international fin trade places an incredibly high monetary value on their large, sleek dorsal and tail fins for luxury soups.
And there is even a highly specific, localized threat in regions like Thailand. Those beautiful, hardened, thorny ridges on their heads.
The armor they use to fight off tiger sharks.
Yes, those spikes are sliced off, dried, and intricately carved into ornate rings and pendants. They are sold widely as amulets.
It's driven by deep-seated cultural beliefs that wearing the thorns offers magical protection against dangerous waters or sea spirits.
Which creates a highly lucrative black market. And it puts immense, unsustainable pressure on a population that takes a full year just to have a small litter of pups.
They simply do not reproduce fast enough to offset the rate at which they're being removed from the ocean.
It's a stark biological math problem. But the conservation literature is not entirely devoid of hope.
There are real, tangible actions being implemented right now. Fishing technology is actively adapting.
Yes, many commercial nets are now being fitted with bycatch reduction devices, or BRDs.
Which are incredibly clever engineering modifications.
They are basically built-in, rigid escape hatches sewn directly into the funnel of the nets.
They use a grid system that allows the smaller schooling fish to pass through the bars and be caught.
But when massive, heavy animals like sea turtles, dolphins, or the heavily armored guitarfish encounter the grid, they can't pass through.
The grid physically forces them toward a specialized exit flap, allowing them to swim entirely out of the net to safety.
While preserving the fisherman's catch. It's a technological compromise that saves millions of animals when properly utilized.
Furthermore, the collaborative aquarium breeding programs are doing vital scientific work. By monitoring these pups in controlled environments, biologists are gathering data that is impossible to collect in the wild.
They're learning exactly what nutrients they need, tracking how fast they grow, mapping their genetics, and observing reproductive behaviors.
All of this empirical data is absolutely essential for formulating effective recovery plans for wild populations.
And for aggressively lobbying governments to create properly sized marine protected areas where they can live without fear of nets.
It requires a massive team effort across every discipline.
From the genetics researchers mapping family trees, to the aquarists preparing crab diets, to the everyday people who visit these aquariums and adjust their own seafood consumption to demand bycatch-free products.
Every single action contributes meaningfully to their survival.
And as we reflect on the entirety of this journey we've been on today, from the ancient fossilized teeth of their ancestors buried in rock millions of years ago, to the warm, crackling shores of the Indo-Pacific reefs.
It truly highlights how this confusing half-shark, half-ray hybrid is an absolute masterpiece of ocean engineering.
It really is. It navigates the pitch-black depths using a biological metal detector, breathes through a snorkel while buried in sand, and protects itself with armor-plated skin teeth.
It is a creature that borders on the magical, and it serves a structurally crucial ecological purpose.
As a large predator, it acts as a vital stabilizing force. By hunting the heavy crabs and lobsters, it keeps the reef in perfect harmonious balance.
Without them, crustacean populations could explode, fundamentally altering the health of the entire reef.
I want to say a huge, sincere thank you to you, the listener, for tuning in and for bringing your curiosity and imagination on today's journey. Exploring the ocean is always more rewarding when we do it together.
Absolutely. Unpacking these mysteries reminds us of our responsibility to understand and protect this web of life. And a special thank you to Ben for co-producing the episode and helping bring this magnificent story to life.
Yes, thank you, Ben. And before we sign off, I want to leave you with one final thought to mull over.
A reflective idea.
Think deeply about how the bowmouth guitarfish evolved over millions of years. Every curve of its body, the specific dynamic color of its spots mimicking the mangrove shadows, the exact shape of its crushing teeth.
It was all perfectly shaped to match its home.
Exactly. The animal is quite literally a biological mirror reflection of its environment. If an animal's physical body is shaped so intimately by the world it lives in, how do you think we can consciously shape our own human world to ensure that masterpieces of evolution like this always have a safe, thriving place to call home?
A profound question to end on.
See you next time on Saltwater Stories.